So, welcome to the PhD session. So we have 90 minutes, but one additional speaker. So either we run 20 minutes late, or each speaker cuts a little bit the time, but typically it's equal. I do understand this, right? Okay, but so the PhD session is about that the master students could see what PhD theses are, what subjects we have. Maybe they're motivated to also try to get a PhD with us, because we're always interested in getting smart PhDs, right? And you know my position, right? If you want to earn a lot of money, you must get a PhD. And today we start with the first smart guy who wants to earn a lot of money. It is Sebastian Lehrig from the University of Paderborn. And the talk will be about the architectural template method, design time engineering of SaaS applications. Sebastian, I'm looking forward to your talk.
Thank you. It does work. Okay, thank you, and thank you all for participating in the PhD session, especially on my topic, which is called the architectural template method. It's an engineering approach for software as a service applications. And the purpose of this talk is not to introduce you to that method and what I want to do with that. I'd like to start with a small example of a software architect who wants to design an online cloud bookshop. He has a special requirement for that, an elasticity requirement. You should know a lot of that now. So the elasticity requirement states essentially that independent of the workload here, you want to have constant response time on the y-axis of this graph. So that's the requirement he wants to fulfill, and a really smart software architect who doesn't like a lot of risks. So he wants to ensure already at design time that this requirement is met. He has a look in the literature to find out whether there's any engineering approach that provides him this capability. And he finds something called model-driven performance engineering. That's the approach he wants to use now to analyze at the design time whether this requirement can be met for his application. So how does that work? So essentially the architect starts in with model-driven development. So he has to specify some models. These models, they have to capture the performance relevant stuff of this application. So one of these models is a consumer model. How do the users behave of this online bookshop? There can be a relatively low arrival rate of consumers, and there can also be something called peak scenarios, where suddenly a lot of people approach this online bookshop, maybe because there's a new best-selling item, or it's Christmas time and everybody wants to get presents. So he has to model that somehow. Of course, he has also to model the software structure at design time, also the behavior of the software. He may decide for a three-layer architecture here, the web front end, an application logic component, and a database access component. And finally, he has to model the environment where he plans to deploy that application into. In our case, that's a cloud computing environment, for instance, Google App Engine. So, and now in model-driven performance engineering, you can take that model, this set of models as an input, run an analysis tool, and predict whether this requirement is fulfilled. And now we are still at design time. We just have to model it. So you could get a result like this, which would yield this requirement is not met. Then this analysis results also point to the place where this went wrong. So the analysis result could state that the logic component is a bottleneck resource. So you should somehow fix that. And you have to look at cloud computing patterns.org, finds an elastic load balancing pattern, and finds out, okay, I should make the logic component somehow stateless.
You already passed. Since you mentioned that.
Okay, so he makes the logic component stateless. Then he can safely replicate the component and use additional cloud computing resources to achieve that load balancing. So he modifies the model, still at design time. He reruns the analysis, and something, of course, he gets that his requirements fulfilled. And he's quite happy. Then he continues to implement and test the application. That is an engineering method for designing such applications, which exists already. Also quite accurate. Analysis results are really good. Follow that approach. However, there's one problem with that approach, and that is why most of you will not know this approach. Creating such models requires a lot of effort. You have to be a performance engineering expert for creating such models. They are heavily complex. Let me give you one example for the complexity involved here. So for replicating the logic component, these approaches allow you to specify model transformation rules in an imperative form. I have one of this imperative specifications available here that are so-called story diagrams. You don't have to understand them in detail. But for this simple rule I've shown to you, it's already that complex. Even though essentially what we want to state is something like that in a declarative form here. If there is also a constraint, for instance, the logic component somewhere identified here has a utilization of over 80%, that is somewhere identified there. Then we want to add a new load balancing instance to the load balancing strategy. That is done somewhere there. Okay. However, it's still that complex on the left side, and we have to do that over and over again whenever we want to use something that's related to load balancing. So we tell that to the architect that he has to do all this modeling stuff. And he asks, do I really have to model all of that? That's strange. I mean, we have reoccurring patterns for workloads. You find that among cloud computing patterns. Or we have reoccurring software patterns, like the Elastic Load Balancer. And we also have reoccurring environments, complete environments, where you actually just want to say, okay, I want to use that service. I don't want to be an expert in how the service is implemented. For these approaches, you have to be an expert. And that's kind of a bad situation. I call that the problem that the effort for modeling is higher than the risk of following the try and pray approach, meaning nowadays the architect would just try to implement the whole thing, test it in the environment, pray that it works, and if it doesn't, he has to start all over again. Okay, so now I can come to my outline. The problem I'm tackling is the modeling effort versus try and pray risk. The idea I have is to create a templating mechanism that allows you to specify all the recurring stuff into little puzzle pieces, but leaving some gaps open, and only these gaps have to be filled out by the software architect. That is all the application-specific stuff that doesn't reoccur over and over again. The foundations for that, so these are patterns that are really specified to performance engineering. That's why I have as a foundation performance engineering and some related work on performance engineering in my work. I will also provide a plan of how I want to evaluate my method, and including the time when I want to achieve what. And I will conclude the talk with a summary. Okay, so now that you all get the problem I'm tackling, let's see what is my idea. So the idea is that we observe there are so many recurring things, so I try to provide patterns that reflect that. So I could have a reusable pattern for varying workload. Maybe it's fully specified such that the architect doesn't even have to specify anything more. I just want to use that pattern. That's not possible on the software layer here. There I can only have something like half specified. I know there the structure, it's a three-layer architecture, and this is the presentation, the middle, the data layer, but I don't know how the concrete component would look like. It's application specific, so I would have to specify, so only the architect has this knowledge, I cannot make that reusable. And of course I can think of patterns for the whole cloud computing application. So the idea is now somebody smart creates such templates, puts them inside a catalog of templates called the architecture template catalog, and then the architect is provided with this catalog. Having this catalog at hand, you can just select a template from this catalog. That's a composed template out of the previous three templates, called the three-layer Google App Engine template. And then you just have to fill out the missing parts that are really application specific and that only he knows. And then the rest is as before. So you use our analysis tools to work on the software architecture, and once we are satisfied, we implement the tests over it. The benefits you get by that is you are provided, or software architects are provided with reusable best practice templates. So experts create these templates, they can be reused over and over again. And thereby we end up in a way more efficient engineering approach compared to all previous approaches. As we will also see, it's more declarative than previous approaches. Finally, we end up in a world where we can conduct early quality analysis from an economically seen perspective, so the effort is now lower. Let's have a look at a template. How would such a template concretely look like? So remember this adaptation rule. On the left side, the imperative one, on the right side, the declarative one. Assume we want to create a template for this three-layer architecture. And we want to have a scalable middle tier that has this elasticity capability we talked before about. So how would that look like? So the middle layer somehow needs to have a specification of an adaptation rule that would become a parameter of that part of this template. The architect has then to specify the adaptation rule as well as the concrete component that will be filled into that place in the pattern. And the last thing he has to do is he has to link these two specifications to the template. I have an annotation mechanism for that allows you to annotate architecture description languages with such specifications, and essentially it states that these two items above are now assigned to the middle layer. Thereby we fill out the template. That's all the architect now has to do. It doesn't have to cope with this strange imperative implementation anymore. Another question is now, why does that still work with analysis tools? And here the idea is to use so-called performance completions that are basically a generator that just takes that as an input and then generates this imperative description. The information we got is enough to generate such a description. And then it's understandable by all the analysis tools that currently exist. Sorry?
Okay, what do you do, Palladium?
I'm extending Palladium. I'm one of the popular developers. Okay. So my work directly goes into Palladium. I would also say that. Next. That's coming to the foundations now. So foundations are related to performance engineering. That includes the old process, which was already introduced in 2002 by Connor Smith in a book about performance engineering. So that's quite an old process. There's also some tooling that makes use of that process. Palladium, where I'm one of the core developers, right? There's also an extension of Palladium called Simulator. So Palladium is a software simulator. Palladium takes these models I've introduced as an input and can simulate that. And Simulator adds the capability to Palladium to model self-adaptations and to analyze them. Still there are some things missing. So first of all, currently it's not possible to model dynamic workloads where depending on the time we observe a different consumer. So sudden peaks can currently not be modeled in Palladium, which has also the consequence that elasticity properties have only limited support. That's why my colleague and I, Matthias Becker, he works on Simulator. We fix these issues currently, and that goes into Palladium. It will be fixed soon. So that's currently our top priority. Besides that, the related work of architecture templates consists of two categories. First is our architecture description languages that allow to specify architectural constraints which are needed for my templating mechanisms. There are some architecture description languages. The most famous one is ACME, which is a relatively old one. It allows to specify architectural styles, for instance, which is quite similar to some patterns I had a look at. Other authors, they specify similar constraints using ontologies or the Z specification language. So Abbott and others use the Z specification language. Paul and others, they use ontologies. The other category are design time analysis. We have already seen later in Simulator. The Clever is a similar approach, and below you also see the work of Jens Happe and others. They have introduced the performance completions I used to generate the iterative stuff. Yeah, obviously my approach is somewhere here in the thing where nobody settles at the moment. That's new to combine the ideas of architectural constraints with performance engineering approaches. Okay, so that were the foundations. Now just a brief look at my evaluation plan. So I structured the 3 minutes. Okay, that's good. I structured my evaluation into several levels. Level 1 evaluation has a look at the metrics, whether they are good. Here I want to provide support for elasticity metrics inside Palladium and Simulator. I want to investigate the accuracy of the metrics and the reusability of my templates. Here I want to use some simple case studies that assess these criteria. In this validation, I also have to work on the concepts, examples, meta models, and editors for architecture templates. That's all the stuff I'm doing here. That's the starting point, essentially. The level 2 evaluation has a look at the applicability of the approach. Here I want to conduct industrial case studies with the partners in my project. I'm working with the Cloud Scale EU project. SAP and Ericsson are partners. They would like to use my patterns, so it's a perfect scenario for giving it to them and then getting industry case studies for free. I want to assess whether they can reliably specify the input and whether they can meaningfully understand the output of the analysis. And the most complex evaluation is the level 3 evaluation, where you evaluate the benefits of your approach. Here I want to conduct a controlled experiment that compares my method against competing approaches. The naive approach would be to choose the performance completions. I built on for that. Okay, the timeline states that I start from top to bottom. Here I need 2 years. I passed the middle of that, so I have roughly half a year left for finishing with level 1. For the rest, I planned half a year each. Coming to the conclusions. So, I've shown to you an engineering approach for software architects that heavily reduces the effort in modeling such performance models. Thereby I provide reuse mechanisms that allow them to make use of best practices, such that early quality analysis become now feasible and can actually also arrive in practice. So my boss always says good PhD theses always raise more questions than they solve. So there you go. Write me either an email, have a look at our project page, Cloud Scale Project EU, or directly ask me here. At best now, I'm happy to answer. Thanks.
Thank you very much, Sebastian. Are there any questions? I have a non-expert question.
Okay, this is always good on start.
Okay, so not being really an expert in these environments and so on, but it seems to me that some of the functionality, except probably the performance part of it, is also available in other environments, like Open and Tosca, for example. How do you differentiate?
Which parts you mean?
I mean, the idea of the template, the idea of
Same name, different things.
right. Oh, okay. So can you explain to us why it's the same name, different things?
The main point is that the current templating approaches they don't have any support for design time analysis like we do in Palladium. That's something which is missing, that you just have templates enriched with performance properties that allow you to do the analysis like we do. Like we do. Yeah. So current template mechanisms are more focused on the structure of your design. For instance, you can provide a template for, like I also did for a 3-layer architecture. You have some constraints. You're not allowed to connect presentation components directly with data access components. So templates can cover that, or patterns or styles. Yeah, it's all related. But they cannot be analyzed directly. And that's included in these templates by making use of these performance completions. So that's really good. Okay.
A few slides back, you had 3 levels of work that you are doing exactly. Can you give me just an example of accuracy, some of your metrics over there, yeah, in the first level? Accuracy of metrics, what metrics, elasticity metrics you are having in mind?
Okay. So first of all, it's not only elasticity we investigate, we differentiate between scalability, elasticity, and cost efficiency. So for each category we provide metrics. For each category we currently have a set of around 3-4 metrics we want to investigate. One metric is shown in the graph. So we want to investigate the response times for varying workloads. That's one metric. Then, because we have support for self-adaptations, we can also detect SLO violations, and we can just count them. And the more SLO violations you have, the worse is your elasticity capability. That's another metric.
How do you get that metric? Basically, it's the function behind the diagram. How do you get to the data?
With Palladium. See a stupid answer. I have somewhere a backup slide. Let's see. So that's a brief overview of Palladium. The left side of Palladium is basically the input model I have also used. So that would be the model that is used as an input. That's Palladium, and it can generate a different set of analysis approaches. You have analytical approaches that use stochastic irregular expressions or stochastic process algebras. They can be run quite efficiently, but they are less accurate. The main thing we focus on are queuing networks that are simulation-based approaches. That means I generate a simulation out of my model and I just run it. And I add a set of probes to that simulation. Then I can get a lot of measurement points, and based on that data I can generate the graph.
So this will, as far as I can see, this will only work for pure code. If you have embedded SQL, for example, I can make the SQL as complex as I like, and I guess you have no chance to figure out what the runtime situation is.
Yes, that's true. So after your design, you can, of course, do a lot of bad things you did not cover in your design.
But so just maybe just comment.
We can continue
it's for code only. For code, for Java code or any kind of program code. Bare code, or I don't know how to call it.
It's a very nice discussion for the next coffee break.
Okay.
Yeah, in the interest of time, I'm sorry. Yeah. Thank you very much.